Chapter 8. Probability Distributions. There are two possible outcomes when flipping a coin, head or tail. We can assign the number 0 to the outcome head and the number 1 to the outcome tail. This produces a variable that takes one of two values, either 0 or 1. Chance will determine the value of this variable. Such a variable, called a random variable. In general, a rule that assigns one and only one real number to each outcome in the sample space is called a random variable. Random variables can be classified as discrete random variables and continuous random variables. A discrete random variable assumes finite or infinitely countable numbers of values, while a continuous random variable assumes values in an entire interval or union of intervals. We now give some examples to illustrate what we mean by a discrete random variable. In this example, we roll two different dice. The sample space contains 36 possible outcomes. If x is the sum of the dots obtained where rolling the two dice, then this sum is a discrete random variable. Its possible values are 2, 3, 4, up to 12. In this example, we toss a coin repeatedly until a head turns up. The number of tosses required is a discrete random variable. This random variable assumes infinitely countable values, 1, 2, 3, 4, 5, and so on. To introduce the concept of a probability distribution, we start with the following example. We toss two coins, a penny and a nickel, and we are interested in the number of heads obtained. The number of heads is a discrete random variable that can take the values 0, 1, or 2. Since the coins are fair coins, the probability of obtaining 0 heads is 1/4. The probability of obtaining 1 head is 1/2, and the probability of obtaining 2 heads is 1/4. In this way, we obtain a correspondence that assigns probabilities to the values of the random variable. Such correspondence can be represented in a table, and it is called probability distribution. Whenever possible, we usually, instead of a table, we use a function, which gives us a formula that we can use to calculate the probability for each possible value of the random variable. In the previous example, we can use the following function f of x equals combinations of 2 taken x at a time, divided by 4, for x equals 0, 1, or 2. If we use f of x to represent the function that assigns probability to the random variable that takes the value x, then f of x must satisfy two conditions. 1. F of x takes values between 0 and 1 inclusive. 2. The sum of the values of f of x take over all possible values of x equal to 1. In part A of the example, the values assigned to 1, 2, and 3 are 0.51, 0.26, and 0.32 respectively. Each of these values is a number between 0 and 1, so condition 1 holds. But when we add these values, we obtain 1.1, which is greater than 1, so condition 2 fails to hold. Therefore, this is not a legitimate probability distribution. In part C, the values are assigned to 1, 2, and 3 are 10 over 33, 1/3, and 12 over 33. Each of these values is a number between 0 and 1, and when we add these values, we obtain 1. Therefore, the given values serve as the values of the probability distribution of some random variable. In example 4, we can start by evaluating the function for x equals 1, 2, 3, and 4, and get the values 3 over 18, 4 over 18, 5 over 18, and 6 over 18. Each of these values is a number between 0 and 1, and the sum of these values is 1. Therefore, the function f of x determines a probability distribution for some random variable. One of the most important discrete probability distributions is the binomial distribution. The binomial distribution arises when an experiment with two possible outcomes, success and failure, is repeated n times independently. In this case, we say that we have n independent trials. The probability of success in each trial is the same, and it is equal to some number between 0 and 1, say p. This means that the probability of failure is 1 minus p. The number that represents the number of successes in n trials is a discrete random variable. This random variable can assume the values 0, 1, 2, up to n. The probability of getting x successes in the n independent trials can be given by the function f of x equals combinations of n taken x at a time times p to the power x times 1 minus p to the power n minus x, for x equals 0, 1, 2, up to n. This random variable that represents the number of successes in n independent trials is said to have a binomial distribution with parameters n and p. It is important to know that the binomial distribution can be used only under the following assumptions. 1. We have a finite number of trials. 2. The probability of success does not change from trial to trial. It is fixed and equal to the same number for each trial. And 3. The trials need to be independent trials. In this example, each person shopping at this store either takes advantage of a promotion or does not take advantage of the promotion. Probability of success is the same as the probability of taking advantage of the promotion, which is equal to 1/3. And probability of a failure is 2/3, since we are considering 3 persons. The number of trials is 3. In this case, we use the binomial distribution, with p equals 1/3 and n equals 3. And the probability that x persons take advantage of the promotion is f of x equals to combinations of 3 taken x at a time times 1/3 to the power of x times 2/3 to the power of 3 minus x. To find the probabilities, we evaluate the function f of x for the values 0, 1, 2, and 3 persons. The corresponding probabilities are 8 over 27, 12 over 27, 6 over 27, and 1 over 27. We can use these values to construct a histogram for the distribution. In this example, we toss a fair coin 10 times. What is the probability of obtaining exactly 4 heads? Each flip of a coin represents a trial, so we have 10 independent trials. If getting head represents success, then because the coin is a fair coin, the probability of success is 1/2 or 0.5. We can use the binomial distribution with n equals 10 and p equals 0.5 to calculate the probability of obtaining exactly 4 heads in 10 flips. This probability is given by f of 4, which is equal to combinations of 10 taken 4 at a time, multiplied by the product of 0.5 to the power 4 and 1 minus 0.5 to the power 6. Using a calculator, we can see that the answer, rounded 3 decimal places, is 0.205. The same answer can be obtained by using the table for the binomial distribution. This is Table 5 on pages 503 to 507 in your textbook. In this example, the 10 rocket launchings represent 10 independent trials. If by success we means that a rocket launching has to be delayed, then the probability of success is 30%, or 0.30. We can use the binomial distribution with n equals 10 and p equals 0.30. In part A, we want to find the probability of x less than or equal to 3. This is the same as the sum of 4 probabilities. Probability of x equals 0, probability of x equals 1, the probability of x equals 2, and the probability of x equals 3. We can find these probabilities from Table 5. Then we add them up to get the answer 0.649. In part B, we need to find the probability of x greater than or equal to 6. In a similar way, and by using Table 5, we get the answer 0.047. Now we consider another discrete distribution, the hypergeometric distribution. This distribution arises when a population can be split into two parts with different attributes. If the first part contains A objects, we call successes, and the other part contains B objects, we call failures, then the population size is uppercase N equals A plus B. If a random sample size, lowercase n, is taken from the population, and x represents the number of successes in this random sample, then x has a hypergeometric distribution with parameters a, b, and n. To find the probability of getting x successes, we divide the number of favorable outcomes, which is the product of combinations of a taken x at a time, and the combinations of b taken n minus x at a time, by the total number of outcomes, which is combinations of a plus b taken n at a time. In this example, we have two kinds of solar collectors: 12 flat plate collectors and 8 concentrating collectors. From these 20 collectors, 6 are selected at random. We want to find the probability that 3 of the 6 collectors are flat plate collectors. This situation can be modeled by using the hypergeometric distribution, with a equals 12, b equals 8, and n equals 6. Using the formula for the hypergeometric distribution, when x equals 3, we get the answer, which is 0.318 rounded to 3 decimal places. This problem can be solved by using the hypergeometric distribution. The 12 male applicants can be split into two groups. In the first group, applicants have working wives, and there are 9 applicants in this group. In the second group, the applicants have non-working wives, and there are 3 applicants in this group. In this example, we can model the situation by using the hypergeometric distribution with a equals 9, b equals 3, and n equals 2. To answer part A, we let x equals 0 in the formula of the hypergeometric distribution. The probability is 1 over 22. In part B, we let x equals 1 in the formula to get the probability 9 over 22. And in part C, we let x equals 2 to get the probability equal to 12 over 22. If we have a hypergeometric distribution with the parameters a, b, and lowercase n, and if the population size a plus b is large as compared to the sample size lowercase n, then we could use the binomial distribution to approximate the hypergeometric distribution. The parameters of the binomial distributions, and in this case the lowercase m and p, equals a over a plus b. This approximation should be used when the sample size lowercase n is less than or equal to 5% of the population size. In this example, the population size is 200. The population is split into two parts. One part contains 120 union members, and the second part contains 80 employees that are not union members. What is the probability that 3 out of 6 randomly selected employees are union members? The hypergeometric distribution can be used here, with a equals 120, b equals 80, and n equals 6. In part A, we want to find the exact probability. We just let x equals 3 in the formula of the hypergeometric distribution to get 0.280. In part B, the binomial approximation can be used since the sample n equals 6 represents 3% of the population. Using p equals 120 over 200, which is 0.06, and the binomial table, table 5, we find the probability is approximately equal to 0.276. Another important discrete type distribution is the Poisson distribution. This distribution arises when they are interested in the number of times a particular event occurs in a certain time interval or a certain region. Some examples include the number of phone calls received by an office during a 1-hour period, and the number of field mice per acre. If lambda represents the expected number of events, then the probability that x events will occur can be given by the function f of x equals to the product of e to the power negative lambda and the lambda to the power x divided by x factorial. In this example, the number of complaints has a Poisson distribution with lambda equals 3.2. To answer part A, we replace x by 2 to get the probability, which is equal to 0.2087. To find the value of e to the power negative 3.2, we can either use a calculator or use table 12 on page 517 of your textbook. In part B, we want to find the probability that x is less than or equal to 2. This is the same as the sum of probability of x equals 0, probability of x equals 1, and probability of x equals 2. We find these probabilities by replacing x in the Poisson formula by 0, 1, and 2 respectively. After performing the calculations with the help of a calculator, we get the answer 0.3799. Here we have another approximation. Probabilities involving the binomial distribution can be approximated by using the Poisson formula. If we have n independent trials with probability of success p, then the probability of getting x successes among n trials can be obtained by using the binomial distribution. However, if n is large and p is small, the probability can be approximated by using the Poisson formula with lambda equals np. This approximation should be used only when n is greater than or equal to 100 and np is less than 10. In example 12, we are studying 150 licensed drivers. So the number of trials is n equals 150. The probability of success, that is the probability of involving in at least one accident in a given year, is 5%. So p equals 0.05. The number of drivers involving in at least one accident among 150 drivers has a binomial distribution with n equals 150 and p equals 0.05. However, to answer the question, we can use the Poisson approximation to the binomial distribution, letting lambda equals np, which is equal to 150 times 0.05, or 7.5, in the Poisson formula. We compute the probability of x less than or equal to 2. The answer is 0.0202. We usually refer to the expected value of a random variable as the mean or the mean of the probability distribution, and we denote this by using the Greek letter mu. If the random variable takes the value x with a probability f of x, then mu equals the sum of the product of x and f of x over all possible values of x. The variance of a random variable, denoted by sigma squared, is defined to be the sum of the product of x minus mu squared and f of x over all possible values of x. An equivalent formula for the variance is given here. This formula is more convenient when we calculate the variance. The population standard deviation is defined to be the square root of the variance. This slide summarizes the different probability distributions that we studied so far, and gives the mean and the variance for each of these distributions. In this example, a probability distribution is given. The random variable takes the values 0, 1, 2, 3, or 4, with the probabilities 0.2, 0.5, 0.1, 0.1, and 0.1 respectively. We use the formulas for mu and sigma squared to obtain the mean and the variance of the probability distribution.